So, my name is Dennis. I'm working for Western Digital, and I'm going to present you now the next half an hour my talk about supercharging the cloud with own storage. What is the talk about? So we have conventional SSDs, but they do not perform consistently and predictably on a larger scale. Latency and throughput is affected when we reach the steady state of the disk. You can over-provision conventional block devices, and that mitigates that effect a little bit. But zone storage that Andreas also addressed in his talk was invented to get rid of that downside. So the agenda for this talk, I'm gonna give quick introductions for Kubernetes and zone storage, but a little bit different what Andreas did. Then we will talk about containerized persistent storage and our work on enabling zone storage as a first-class citizen in Kubernetes workloads. And at the end, live demo. Yes. Let's see if that works. Okay, yeah, as a motivation, let's try to get a feel why Kubernetes and why that is an interesting candidate for zone storage. So cloud-based workloads take over the industry right now. Everybody is moving towards containerized applications and to just take the advantage of the cloud model. Kubernetes is the leading container orchestration software, and there is a CNCF annual survey, and they asked companies how much they are using Kubernetes, and the surveyed companies were saying 44% of their work applications are mostly containerized. And also in that year, workloads increased by 30% and auxiliary workloads even by 211%. So, and on the other hand, we have zone storage devices, which comes in the form of SMR HDDs, which give capacity benefit over conventional HDDs. And we have the ZNS drives, which offer roughly 3 to 4x higher performance with 7 to 28% of higher capacity. And also usage of QLC in write-heavy workloads. So, and zone storage is already deployed heavily at hyperscalers and in larger storage clusters. The purpose of this talk is to enable Kubernetes to seamlessly take advantage of the remote zone storage without the end user to have the necessity of changing their applications. So moving on, quick introduction to zone storage. Andreas was presenting you the zone storage model already, and we can see here a benchmark scenario where we have 3 different drives, 2 conventional block devices and 1 ZNS SSD, and they are each 2 terabytes large. We write them and overwrite them over a certain period of time, and we can see after we have reached the steady state after overwriting the drive and after writing the drive once and then start overwriting, we see throughput is dropping in the conventional block devices. That's due to the internal garbage collection. ZNS SSDs do not have that internal garbage collection because you have that interface facing to the user, and the user has to decide when to delete a zone. So we get that consistent performance. The catch is, of course, writes must be sequential within a zone, and the software layers need to support that behavior. The zone storage Linux ecosystem, as of today, we have zone storage hardware at the bottom, coming in the form of SMR disks and ZNS SSDs. We have Linux support. We also have support in local file systems, like for example Btrfs. We have user space libraries like SPDK that support zone storage, and also distributed storage solutions and databases. But the focus of this talk is in the cloud orchestration box, Kubernetes. And that's next up. So, small Kubernetes 101. Kubernetes is a cloud container orchestrator. It basically provisions resources for your containerized workloads. Why do people use it? Well, because of fault tolerance, they can scale on their hardware fleet, and there's cost optimizations through effective resource usage. So on the right-hand side, we see a Kubernetes example cluster where we have 3 hardware nodes, and each of those nodes come with resources like CPU, memory, and also storage. And Kubernetes is then just provisioning the resources according to the applications you want to run in that cluster. It was initially optimized for stateless applications, but people want to keep their data and want to use databases, so there is also persistent storage. Let's look at a small example, simplified example here. We have our Kubernetes cluster, and you can chunk up that cluster in multiple different namespaces where you have your independent applications. And for example, we have a web service that is accessed by a user through an ingress, and that web service has 2 containers spin up, which are the same container for fault tolerance. And in Kubernetes, you call a container a pod. That's just a wrapper around the container. And if one of those pods dies, the storage inside of that pod or container is ephemeral. That means we've lost everything. In case a pod dies, Kubernetes goes ahead and reschedules that pod. So we have that fault tolerance I talked about. That web service then might want to talk to a database service like MySQL, which also spins up 2 pods for fault tolerance. And those pods access then persistent volumes through a persistent volume claim. And those persistent volumes are defined through storage classes, like for example Longhorn, OpenEBS, CSAL, or Ceph, which then might or might not support zone storage. So let's see what kind of persistent storage solutions there are. We have the cloud native landscape. You might have seen that diagram. It's huge, and I have zoomed into the storage section here. And to access persistent storage, you need to implement a container storage interface. And that container storage interface is defined through the Kubernetes storage special interest group, and it's basically a gRPC specification. If you implement that gRPC specification, you will get a CSI driver, a container storage interface driver, that acts as a plugin for Kubernetes. So it is not in tree of the Kubernetes repository. And this driver is then there to manage data placement, reliability, quality of service, and of its storage it handles. Yes, and you have multiple different solutions to pick from. There are many that are open source, but also each cloud vendor has their own solution or hyperscaler. The ones that are circled red are having zone storage support in one way or the other, and we are gonna look at some of them now. We can divide those solutions into 2 different categories. One for distributed storage systems that aggregate a local storage of each of the physical cluster nodes. That is, for example, Longhorn or OpenEBS's Mayastore. And then we have storage solutions where you can run them on a dedicated storage node like SPDK's CSAL or Ceph, There was some work from my colleague Arvind going into Ceph Crimson OSD to support zone storage natively, but that's worth its own talk and won't be covered here. So what do those container storage interfaces or these drivers give you as a user? So Longhorn and CCell will provide you with a generic block device or a file system abstractions using underneath a zone storage device if you choose to use those. With Mayastore, we made it such that zone storage devices can be explicitly exposed to the container. We will see that in the live demo later too. So jumping into the first storage solution, Longhorn is a distributed storage system that for persistent distributed storage with no single point of failure. And we can see on the right-hand side that we have our SSDs in our physical nodes, and those SSDs are then communicating to the replica through the file system abstraction. When you spin up a pod and request a volume in Longhorn, Longhorn will spawn an engine, and that engine then communicates through loopback or through iSCSI to a different node replica and gives the consumer a POSIX-compatible file system to work with. So the necessities to deploy zone storage is basically you need to deploy ButterFS on between that layer here, between replica and SSD. So the effort that was previously going in pays out now in the Linux ecosystem. Yeah, and minimal configuration needed, and then it just works out of the box. Moving over to Mayastore, OpenEBS's Mayastore, written in Rust. I also got Rust in my presentation. So yeah, it's much like Longhorn, a persistent, highly available container attached storage solution. And instead of utilizing the file system abstraction, it utilizes SPDK. So the reason behind that is to avoid storage-related kernel modules in order to have node uptime. So they don't want to mess up any API calls to some modules and then bring down some kernel module, and they rather do it in SPDK. And if that happens, they don't care. The pod dies. Kubernetes can just respawn that pod, and the applications that live on the node that have nothing to do with that don't notice anything of that. Let's look at that I/O path here of Mayastore. So we have at the top our consumer that connects to an NVMe over Fabrics target, and that can be on any cluster node. Then on, let's say, cluster node B, we have our Mayastore. They call it a Nexus NVMe over Fabrics target. That's where all the I/O is going to. And that Nexus target is responsible for replicating the I/O. That means in that case, we have 3 replicas. One might live on the same node as the Nexus itself, so it uses loopback. And then 2 other replicas might live on completely different nodes, which then go over the network, also via NVMe over Fabrics. So there was some ongoing work from my side in plumping up zone storage support in Mayastore. But the first proposal is with replication factor 1, because there are also interesting challenges with zoned replication. For example, we have to make sure to keep the zones right pointer across the replicas in sync. Also, what happens on I/O errors. And last but not least, there is also how do we chunk up zone block device into different resource entities. Also, there is an ongoing ongoing community work to rework that interface down here with the SPDK logical volume pool to just have a more flexible interface to interact with the SPDK BDEV directly instead of going through that logical volume pool. And that's also a reason why in the demo I'm kind of working around some things, but you will see that. So the CSI driver consumer will then receive that NVMe over Fabrics target, which is zoned, and then can work with that. The last storage solution is CSAL, which stands for Cloud Storage Acceleration Layer. You might have heard of it in SPDK BDEV FTL, and it has a work in progress patch which adds zone support for that. But what is CSAL? So CSAL is basically FTL that has a conventional high performance block device in front for metadata, and then it writes out the data that was written to that high performance block device sequentially to the ZNS device, and therefore we are hiding that sequential write constraint of zone storage. Yes, and there is also an SPDK container storage interface, and it basically acts like Longhorn. We can spawn pods on different nodes and access through NVMe over Fabrics that CSAL target on a different node. And as a user, you will then receive in your pod that conventional block device over NVMe over Fabrics. Okay, with that out of the way, it's time for the live demo. And gonna explain you quickly the setup here. It's also a simplified explanation. So we have a Kubernetes cluster with one worker node here, and with one master node and 3 worker nodes. On worker node 2, I am deploying a FIO test container, which then attaches to the different storage solutions I mentioned, Longhorn, Firestore, and CSAL. And those devices, those ZNS devices, are attached on a different node. And we force that I/O over the 100 gig network that is attached between those worker nodes. For Longhorn, we are exposing basically the file system backed by a ZNS SSD, ZN540. For Firestore, we are natively exposing the ZN540, and for CSAL, we are having Optane drive as the cache and the ZN540 as the backing storage device. So let me try to get the live demo up here. Yeah, I have a backup here in case something goes wrong, but I'm confident. Yeah. I jinxed it. Yeah, probably not. So I SSH'd into our cluster in the Copenhagen office, and that's my demo master node. And I can quickly show you the YAML file, how the test pod looks. So we can see here the first entry is the persistent volume claim for Longhorn via butfs. It basically just uses the storage class and specifies how much we want. For the CSAL SPDK CSI, same story, storage and storage class. For Firestore, I'm doing a kind of workaround. I have to manually attach the NVMe over Fabrics target from the worker node 3 to worker node 2, where that test container is running later. And here is some boilerplate code for attaching that local device in the container that I'm spawning in a second. You can see here I have that connected NVMe over Fabrics target on worker node 2 specified. And the demo pod itself is just a Ubuntu image with FIO installed. And we specify here volume devices with a device path. That means we have that zoned block device in our container present. And we specify Longhorn and SPDK with the volume mount. That means we get a file system mount in our container here. Yeah, and some more boilerplate code for actually getting the volumes in. So now I can show you the example FIO job that I created and running in a second. Yep. So it simply writes a little bit of sequential data onto each of the storage solutions. First Longhorn, then CCell or in parallel, and Mayastor, and then we read from it for 60 seconds for each storage solution. So I already deployed that LLC demo YAML file, which spins up the container, and we can see if it still lives. And it does. It's running here as promised on worker node 2. And we can access that container. So we can see here we have the Mayastor zoned nexus as subsystem 1 that comes from that IP. It's NVMe over Fabrics over TCP in that case. We can also see the SPDK CSI target here. And if I do lsblk, oops, we can see that the SPDK target is mounted to that directory, and we have also Longhorn here. Yeah, so it's time to run the FIO job. I copied that in. I set that up before the talk. And now we are running the workload. Let's see what's going on. So we can do some I/O stat. So worker node 2 is the node where we are having our container running. And when we list that, we can see that we have here the Mayastor controller, which comes from that IP. And we can also see that it's zoned. Yeah, and then we can just see what's happening. I hope I'm fast enough, so the benchmark is not over. So doing that also for worker node 3, where we have the device attached for Longhorn, and worker node 1, where we have the CSAL FTL target. So it's probably just waiting for all the writes to finish to Longhorn, as we can see here. And in a second, it should start reading. Yes, here it starts reading. And it does that for a minute now. So it's that easy. You can use zone storage in your containerized applications. Yeah. Yes. Yeah. So that wraps it up basically. I have one more summary slide that I can go through. Whoops. Yeah, so the Linux zone storage ecosystem continues to mature. We have now ButterFS, Longhorn, Ceph, Mayastors, OpenEBS's Mayastor, CCell, and end-to-end zoned applications. Yeah, you can seamlessly deploy your workloads on zone storage now with Kubernetes, and you no longer need to change software stacks to deploy zone storage at a larger scale due to Longhorn, ButterFS, and CCell. Yeah, thanks for having me. Questions, if any? Yes.
It's a little bit stupid question or very simple. You had this throughput or performance conventional SSDs,
Yeah.
zone SSDs.
Yeah.
Once there was some trick or some other fault to tell the hard drive what you don't no longer need the block, or is it not used? Or is it hard to use?
So you mean you mean that case? So what that benchmark should actually show is that if you write long enough to a conventional block device, eventually it needs to garbage collect internally. And that drives the performance down of that drive.
As I recall, I'm not especially scared.
Yeah.
There was some trim or some other operation on the, you could tell SSD what you don't no longer need this.
Oh yeah. That drags that line a little bit into the future then. Yes. So that drop off will eventually happen at some point, but you will just mitigate that a little bit.
This is a random workload, right?
Yeah, that's a random workload.
Random,
Yeah.
but we also see it in other workloads, even for applications that are pretty flash friendly, like RocksDB. So
yeah.
And when you start getting several streams going to the same drive, the conventional drives cannot keep those write streams apart, and you get fragmentation, and you have the garbage collection in space. And you see this behavior.
Yes.
Yeah, and one way to get around it is just by what storage as you need.
Yeah.
You work for a storage company.
It's that easy, just buy more storage. Yeah.
And that fixes it. But if you're having exabytes, petabytes, it makes sense to save a little bit on the storage cost and apply smart software. And that's what most hyperscalers said. Every US, every time hyperscalers do this today, in one form or another, to kind of get the price down to one, or get the market much lower.
Okay, thank you.